All right, hello again. In this video, we are gonna work on section 8.1. It's about linearization of the not homogeneous, non-linear differential equation system. Now I'm gonna work on an example, an important example. So we have a non-linear system again. Sorry for the typo. I just fixed that typo on with my hand. So x prime is equal to x times y minus 1. Y prime is equal to y times x plus 1. And you need to find the linearization of the system at all critical points. And the funny part is, we are going to sketch a phase portrait of the system. Okay, so first of all, what is f of xy? F of xy is equal to x y minus 1, right? G of xy is equal to y times x plus 1. We are going to set these guys equal to 0. So from there, I get x is equal to 0 or y is equal to 1. And from there, I get y is equal to 0 or x is equal to minus 1, right? So what are the combinations which gives both 0? So I can take x0, y0. So 0, 0 is a critical point, right? What else? And I can take x minus 1, y minus 1. Y is equal to 1. So minus 1 and 1. These are critical points, okay? Are critical points. Okay, cool. So, okay, let's find the linearization of these guys. So, first of all, let me find the Jacobian for any point. Okay, so Jacobian at any point x comma y. Let's find the Jacobian for any point. So Jacobian for any point x comma y will be, right, partial derivative of f with respect to x, partial derivative of f with respect to y, partial derivative of g with respect to x, and partial derivative of g with respect to y. And what is that equal to? Partial derivative of f with respect to x is y minus 1. And the partial derivative of f with respect to y is x, right? Partial derivative of g with respect to x is y. And partial derivative of y, g with respect to y is x plus y. Okay. All right. Okay. Now, let's find the linearization at each point. Okay. So linearization at 0, 0. So we should first, okay, I should maybe write u prime is equal to Jacobian times u, right? That's why uv is equal to, sorry, u prime v prime is equal to Jacobian and plug it in 0, 0. If you plug it in 0, 0, we will get negative 1, 0, 0, and 1, right? Times uv. And what is u and what is v? So u is equal to, remember, x minus x star. X star, the x coordinate of the critical points, which is 0, right? So it is x minus 0, which is x. So u is equal to x. And sorry, v is equal to, not y, but v is equal to y minus y star, which is equal to y minus y star is 0, right? 0. So 0, this is 0. Y. Okay. So the linearization is this. Okay. Now, as you see here, we have a linear differential equation system where u and v. You don't have u times v, for example. But u is equal to x, v is equal to y. Okay. All right, this is linearization at 0, 0. Let's find the linearization at negative 1, 1. Linearization at negative 1, comma 1. Okay. So again, u prime is equal to, maybe I should put an arrow here. J times e. I say u, but actually normally this vector is made by u and v, right? So I use u in both settings, so don't confuse that, okay? It's just a matter of notation. So what does this say? U prime v prime is equal to, and now plug it in negative 1 comma 1 in the Jacobian. Remember, x is negative 1, y is 1. Y is 1, so it is 0, and x is 1, negative 1, sorry. So negative 1, and y is 1, 1, and x is negative 1, 0. Okay. All right. Okay. What is that equal to? Sorry. Times uv. And what is uv? And that just uv, sorry. And what is u equal to? X minus x star, and x star is negative 1. So x plus 1. Similarly, v is equal to x minus, sorry, y minus y star, and y star is 1. Y minus 1. Okay. All right, so this is the linearization at negative 1 comma 1. All right, now what are we gonna do? We are gonna sketch a phase portrait of this solution, okay, this system. All right. Okay. First of all, let's find the type of the equilibrium points, or type of the critical points, okay? And to do so, we are gonna need to find the eigenvalues for in each case, okay? So at 0, comma 0, what are the eigenvalues? For the sake of time, actually, I can write the eigenvalues directly. So lambda is equal to 1 and minus 1, okay? Will be the eigenvalues. And since minus 1 and 1 are real and different sign, right? One of them is positive and the other one is negative, which means 0, 0 is an unstable saddle, right? Saddle point. Saddle point, right? Okay. So what about at negative 1 comma 1? What are the eigenvalues here? Actually, okay. Lambda squared minus 1 is equal to lambda squared is I. So lambda equals I and minus I are eigenvalues. And what is this case? This case is purely imaginary, right? So there is no real part. This is all purely imaginary. Whenever it's purely imaginary, let me check my notes to make sure I'm saying correctly. Yeah, it is a stable center. So there is 0 real part. So negative 1 comma 1 is a stable center. Okay. See, we could find the behavior of the solution here. Okay. Now, okay, let's draw the phase portrait. Okay, so I think I can draw it in the next page. Okay. First of all, let's draw XY plane. So let me write down what we have actually from the first page. Don't do that. So what do we have here? X prime equals x times y minus 1 and y prime is equal to y times x plus 1. Let's draw the null lines first of all. Okay. So set this guy is equal to 0. We get x is equal to 0 and y is equal to 1, right? So let me use other different colors. Let me pick green. So x is equal to 0 and y is equal to 1. X is equal to 0 is this, right? And y is equal to 1 is that. So the green is for, so this color is for x nucline. And what about the y nucline? Again, I have set equal to 0. Let me pick another color for y. I pick, maybe I should pick another color, or maybe this color. Okay. Anyway, so y is equal to 0 and x is equal to minus 1. Y is equal to 0 is that. And x is equal to minus 1 is this, right? Let me double check. Okay. First of all, the intersection of these null lines are the critical points, right? Remember the critical points? 0, 0, minus 1, 1, right? Okay. Now, we should first find, as we did in the section, the previous section for the linear system, we need to find the direction of the arrows here, okay? And to do so, we should look at the null lines again. Let's start from the, maybe I can start from second null line, y null line. That null line is dividing our plane into 4 regions, right? This is the first region. Second region is on the bottom left, right? Bottom left is third, and up left is the fourth region. And for example, let's start from this region. When x is bigger than 0, when x is bigger than minus 1, and y is bigger than 0, which is this region, right? Y prime is positive, which means y is increasing, right? That's why the direction on these regions, actually there are 4 sub-regions here. Why there are 4 sub-regions? Because remember, I am interested in this whole region. So y prime is all positive, that's why that is all increasing. Similarly, on the bottom here, it's all negative. Which one is the y is negative, but x plus 1 is positive. So in total, y prime is negative. So direction is this, guys. And here, both y is negative and x minus 1 is negative. So negative times negative is positive. So it is increasing here. And here, what do we have here? x minus 1 is negative, but y is positive, and then x is negative, so it is decreasing, right? Okay. So vertically, these are our directions. And what about horizontally? Let's pick our color. Horizontal, I have to look at x prime, right? Because the horizontal direction is decided by x coordinate, right? And these are, again, the null lines. And the null lines are dividing a whole plane into 4 regions, again, similarly. Here, 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 and there. Then x is bigger than 0 and y is bigger than 1, which is this region, right? It is positive, so x is increasing, which means we are going right. Here, when y is less than 1 and x is bigger than 0, it is negative, so it is decreasing. It's going left. Okay. Here, which part? Top left part. X is negative, right? But y minus 1 is positive, so it's again negative. It's going left. And similarly, on the bottom left, y minus 1 is negative and x is negative. That's why it's positive, so it's going right. Okay. So these are the directions of our arrows. Okay. Now, what about on the null lines? Remember, on the null lines, for example, let's start with the x prime null line. Let me pick another color. For example, I can't pick this color. Okay. For the x null line, whenever x is prime is 0, remember, x is not changing. So only change is happening vertically then. And here, so here on this null line, the vertical null line here, only change should be positive, only change should be vertical. And if you look at this part, the part over the origin, the direction of the arrows are towarding up. So our arrows for the solution are right this way, here. And here it's going this way. Okay? Because look at the arrows, it's going down. And also on this x null line, the horizontal one, it's also vertical, right? Maybe I can also point that direction. And here it is this way, but here it is going upwards, right? And again, for that, just check the directions of the arrows on each region. Okay. So similarly, on the y null lines, whenever y prime is 0, which means y is not changing, so only changing is happening horizontally then. Okay. So on the y null lines, for example, the horizontal y null line, this one, x is equal to, so y is equal to 0. It should be all horizontal. And if you look at the directions, so it is going this way, right? Going right here, right? But it's changing direction here because of that. And on the vertical one, again, if you look at the directions, the directions are here. And here it is this way, right? Okay, nice. We got all the arrows. And now what's next? So what are the critical points? Again, the critical points are 0, 0, and 1, this one, right? So we should find the eigenvectors first of all. So, okay, let me make it smaller a little bit. Come here. Okay, let's come to this. Okay. Now, what are the eigenvalues and eigenvectors? Let's go previous page. Okay. So eigenvalues are 1 and minus 1, 4, 0, 0. Let me pick my blue color again, back. So at 0, 0, this is 0. Eigenvalues are 1 and minus 1. right? So what are the eigenvectors? So let me, for the sake of time, let me find the eigenvectors quickly. But let me first look at the matrix -1, 0, 0, 1, right? So -1, 0, 0, and 1. Find eigenvectors. Okay. So V1 will be, let me go to the next page again. So for lambda 1 is equal to 1, let's say the first one is 1. V1 is 0, 1. And for lambda 2 is equal to -1, V2 is, come on, V2 is 1, 0. But remember, these are the values for u and v. But I need to find the various values for y and x and y. But at 0, 0, u is equal to x, y is equal to u is equal to x, and v is equal to y, right? That's why also for these eigenvalues are actually, and if you just want to convert these eigenvectors to the xy plane, so on xy, we still get the same eigenvectors, right? We still get the same eigenvectors. 0, 1. So v1 is 0, 1. v2 is 1, 0. Okay, so 0, 1 gives x is 0, y is 1, this, right, the horizontal one. And since the eigenvalues are positive, it should be going to the direction of the arrows should be pointing away from the origin, right, as it happens here. And for the other one, 1, 0, it is this x-axis, but the eigenvalues are negative. So what do we have? Then the directions of the arrows are directing through the origin, not away from the origin, but through the origin. Yes, actually we got those arrows already here, right? That's why this point is a unstable saddle point, right? Now for the, okay, maybe I can close that one. For the other one is actually, since it's a complex number, right? It's a stable center. That's why our solution will be a center shape here. So let me, and so we don't need to worry about eigenvectors and eigenvalues because it's complex, right? If it was the real case, then if it was the real case, then we should worry about the eigenvectors. But if it is a complex, then we just need to draw the shape, okay? And since it's purely complex, it's a stable center, right? So let me draw a sample solution. No, not this one. So the sample solution, let me pick this color. Okay. So there is a stable center here, right? So the sample solution will be this way here. But it's also, I mean, if you follow the arrows, it is actually, yeah, making stable center shapes here, I guess, like that. But other than that, if you look at the arrows here, there is this type of solutions as well, right? Going left and going down. And also here, if you just try to combine them, yeah, actually you will get a very weird shape look like. So weird shapes actually. But let me stop here for now. So this is how you find the phase portrait of a nonlinear ODE system, okay? And in the next example, I will work on another system this time and try to classify the critical points. But let me stop here for now, okay? So I will see you in the next video.